We're continuing our velocity addition problems. And in this example, we've got a boat crossing a river, but instead of aiming the boat straight across the river, we're going to aim it at a 30-degree angle. So as measured to the line that goes straight across the river, our boat's going to be moving in this direction. So the velocity of the boat with respect to the water looks like this. 5 meters per second at an angle of 30 degrees with respect to that line that goes straight across the river. We're going to start the same way. We've got an equation that tells us how to add the vectors to get the result. And we're trying to find the velocity of the boat with respect to the ground. If we were in a helicopter looking down, what would it look like the boat was doing? Would the boat be making it over here? No, because as the boat travels in that direction, the water is pushing on it this way. So the boat's actually going to end up over here somewhere. We could call that point D if we wanted to. It's going to end up at point D somewhere. Now I know it's going to be over here because I've already looked at the numbers for this problem. But if the water was going a little faster than this, it wouldn't be there. The boat would be heading in this direction, and the water might be pushing it over here towards point C maybe, if the water was really flowing fast. So it depends on the speed of the water, but I've already looked at the numbers, and I'll show you in a minute exactly how to figure out where the boat's going to land. We'll start with our formula here. The velocity of the boat with respect to the ground, that's what we're trying to find. We're going to add the velocity of the boat with respect to the water. So that's this vector here. And we're going to add that to the velocity of the water with respect to the ground. That's this vector here. And our resultant is going to be this vector. The red vector, the velocity of the boat with respect to the ground. So what I'm going to do, I'm going to take this triangle and I'm just going to enlarge it over here. Or maybe not enlarge it, but draw it so it's a little more clear. So this vector in this direction is the velocity of the boat with respect to the water. And this is some angle, and that's what we're trying to find, those two numbers. So how do we do that? Well, we could get out our ruler and our protractor and be real careful and measure the angle and measure the length, and we'd have our answer. Or we use vector components. In order to use components, we need a coordinate system. So why don't we just pick to the right as our positive x-axis and toward the top of the page as our positive y-axis, since we're used to using that coordinate system. So I make a little table like this. I want to break up all my vectors into x and y components. The velocity of the water with respect to the ground is easy because it's only flowing in one direction. Let's take a look. The velocity of the water with respect to the ground is flowing in the positive x direction, and it has no y component at all. And I'm going to use meters per second for my units for everything. Now, my boat is traveling in this direction. This would be a 30-degree angle, so I can break that up. It's traveling at 5 meters per second in that direction. This is the velocity of the boat with respect to the water. And I want to break that up into an x component and a y component. So there's going to be a y component like this, and an x component that points to the left. The y component is going to be 5 times the cosine of 30 degrees. I got 4.33. And that's in the positive y direction. I'll just put a plus sign there just so I know. The other direction, the x component, is going to be 5 sine 30 degrees, which is 2.5. But that's in the negative x direction. And I use sine and cosine because I'm just looking at a triangle here. I have a triangle, and I know that that triangle, the adjacent side of the right triangle, has a cosine of this angle, and the opposite side is a sine. So I'm ready to add these up. I have 2 minus 2.5, negative 0.5 in the x direction, and I've got 5 cosine 30 degrees gives me 4.33 in the y direction. And so I know what these components are of my resultant vector. So let's go back and look at that. That's this resultant vector. The x component is 0.5 meters per second, and it's pointing in the negative direction. The y component is 4.33 meters per second, and it points in the positive direction. And now I know exactly how that triangle is, and I can find the magnitude of the velocity and the angle using these two sides. The magnitude is 0.5 squared plus 4.33 squared, square root, and that's going to be in meters per second. Inverse tangent of 0.5 over 4.33. Now, did I use negative 0.5 here? No, I did not. I'm taking sides of a triangle. I square the side of a triangle, I square the other side, and I get the square of the hypotenuse. Is the side of a triangle a negative length? No, it's not. So we don't put a negative number there. What about here? I've marked my angle. The angle I'm measuring is this one right here. It's marked on my paper. It's shown right there. When I take that angle, when I want to know the tangent of that angle, I look at the opposite side and the adjacent side. Those are lengths of the sides of the triangle. They are not negative numbers. They have to be positive. When you give your result like this, where you draw a little picture and tell me what angle you're finding and what magnitude of the vector you're finding, right here, it's very clear what you're finding when you draw this picture. Don't put a negative angle. You're telling me this angle right here has to be some value. Well, you can't have a negative angle in a triangle, right? It doesn't make any physical sense. You're probably wondering why we need this equation at all. Well, let's take a look at this example. We've got two cars approaching an intersection. Car A is traveling due east at 50 miles per hour. Car B is traveling due north at 40 miles per hour. And we want to know the velocity of B with respect to A. Now, both of these numbers, the 50 miles an hour, the 40 miles an hour, are measured with respect to the ground, because that's how cars measure their speed, with respect to the ground. We need our equation to tell us whether we're adding or subtracting vectors. We want to know the velocity of B with respect to A. What does that mean? That means if you're sitting in car A, what does it look like car B is doing? Think about that for a second. Well, it looks like it's coming almost right at you. Hopefully not right at you. Hopefully these two cars don't collide at the intersection there. Right? We don't want any imaginary injuries in our imaginary physics problem. We want everyone to go home safely at the end of the day. Let's hope these cars miss each other at the intersection. But it looks like they're coming pretty close. If you're sitting in car A, staring at car B, all you see is it coming closer and closer and closer to you. It looks like it's coming right toward you. So our answer needs to point into the third quadrant like that. It needs to point in this general direction. So the velocity of car B, as measured by a person in car A, is going to equal the velocity of B with respect to the ground plus the velocity of the ground with respect to A. This is our formula. Our formula tells us the first subscript has to be the same, the last subscript has to be the same, and the two in the middle have to match. So let's take a look at what we've got here. We're going to start, I'll use blue again, for the velocity of b with respect to the ground. That's due north with a length of 40 miles per hour. So there's my velocity of car B with respect to the ground. If I plot the velocity of car A with respect to the ground, I get this vector here. And I know that I can flip the subscripts because I don't want the velocity of A with respect to the ground. I want the velocity of the ground with respect to A. And what happens when I flip the subscripts? I rotate by 180 degrees. So this is the same as the negative, the opposite of VGA. VGA must point 180 degrees opposite from this. And the magnitude is 50 miles per hour. The direction is to the left. So you see where this equation comes in handy. This equation told us that we had to subtract VAG or add VGA to get the vector we were looking for, the velocity of car B with respect to car A. Here's our red vector for our sum of these other two vectors. And what do we get? We get a vector pointing up and to the left, which is what we expected. And I'm going to mark this as theta, and we need to figure out those two. So the magnitude of VB with respect to A is going to be 50 squared plus 40 squared square root, and that's going to be in miles per hour. And my theta is going to be the inverse tangent of 50 over 40.